The fastest train ever made reached the speed of 605 kilometers per hour. It was named the Japanese Bullet due to its speed and traveled 4 million kilometers in total, while the Earth's circumference is only 40,000 kilometers. While that is impressive, our engineers designed a prototype for a train that can surpass that speed at 1,000 kilometers per hour, taking you from Abu Dhabi to Dubai in just 10 minutes. Like many other magnetically levitated trains, this train mainly depends on supermagnetic conductors. These conductors are found all over the sides and the base of the train. The first step into reaching a high speed is propulsion. The conductors are placed on the railway as shown. The sum of all of these forces will result in the net force being in the forward direction. As soon as the train reaches the next mean position, switch the electromagnetics to the alternate polarity so the net force is again in the forward direction. By controlling the switching, we can control the train's speed. The next and most interesting step is levitation. This simple figure-8-shaped coil helps achieve the levitation by arranging them in the railway. By looking at this example here, you can see that the force interaction between the magnetic force makes an upward force. If this force is greater than the gravitational force, the magnet will move up. As the magnet moves up, the force between the coil and the magnet reduces, resulting in the upward force becoming equal to the gravitational pull. The magnet balances or the train has achieved levitation. The train levitates at 3.9 inches or 10 centimeters. Logically, the higher the train speed, the greater the levitation force. This means if the train is at rest, it cannot levitate. Of course, the train accelerates using tires that go up to 150 kilometers per hour. Once the train has accelerated to a critical speed, the tires retracts as the electromagnetic force is strong enough to levitate the train. Next is the passenger's satisfaction. This step is called guidance. It basically means that the train should not touch either of the railways, and it should stay on a straight stable path. By connecting the figure-8-shaped coils, the train maintains equilibrium at all times. Now, how does this train function any differently than the Japanese Bullet? The difference in the train model itself is not that different. The only difference in the train itself is the technology used and the braking system. But that's not all. The true difference in this train is the railway itself. Unlike the Japanese Bullet, most of this train's path will be inside an air vacuum tunnel that allows the train to reach its maximum potential.